Okay, sorry for the interruption. Someone came to my door, of course, story of my life. All right, so we were talking about the reactant concentration. So, and we'll actually be talking about this as we get into the collision theory. So, in the increased concentration amount, right? So, as you're increasing the concentration, you're going to increase the amount of collisions that will take place within a solution, right? So, if there are more particles that are in the solution, they're going to react quicker because they're so close to each other, right? So that's going to have more collisions, which therefore is going to increase the rate of reaction. So if there's more of them, they're going to connect quicker because there's an increased concentration of the reactants. So that's those two. So the next one is the surface area. So surface area is increasing the surface area, increases the reaction rate if the reactant is a solid. So, if you increase the surface area, then you increase the rate of the reaction. Oh, you know what? I forgot to continue to write these. Concentration. Okay. So the reactant concentration is what? So if you're increasing the number of particles, right, that are reacting, which are in the reactant, then you're going to therefore increase the rate of the reaction. So increasing concentration is going to increase the rate or the reaction rate. And if you guys don't remember, RxN is reaction. And so then surface area. So if you increase the surface area, you increase the reaction rate, right? So if you have a solid, so basically what they're saying is that the more area that you create on the surface of any type of solid, right, the more this is, in terms of this being round, this is creating the best surface area in this sense, because there's no corners, right? So every area is able to have a reaction. So the more areas that you're able to create reactions with, then the quicker that those reactions will happen, right? So if all of this is open, then it's like, oh, I can create reactions all around here. So this is creating the most surface space, right? In a sense, surface area or space, right? Creating the best shape so that you can have more reactions all at once on the surface, right? So if you increase that surface area, the space in which that area can react with another compound, then you're going to increase the rate of the reaction. So increasing, I'm going to put SA for surface area. Surface area is going to increase the reaction rate. Okay. So the presence of a catalyst. So presence of a catalyst increases the rate of the reaction. Increases the rate of reaction. So as we will discuss later, a catalyst is something that comes in is added into, like, for instance, the solution. And I kind of think about it as like a midway house. So it comes in and it kind of holds everything in its little basket, and it helps to increase the rate of the reaction. Increase the rate of chemical reactions. So it's like it just kind of vacuums in. It's like, okay, you know what? You guys need some help. Let me help you. But then it doesn't get used in the reaction. So it's just like a helper. It's just like, here you go. I'm going to help you out, help you quickly create that chemical reaction you want to create, because I know it's harder for you to do it by yourself. But I don't want to be involved in the reaction. I just want to come and help. It's just a helper. So it's literally, the definition is there to increase the rate of reaction. It's the like catalyst. So you have the present of the catalyst. So a catalyst equals increased reaction rate. Okay, so that's basically what you need to know for each of these areas. So when I would say, okay, well, what are the four, what are the four conditions affecting the reaction rates, right? And like define them. So these would be more than fine, like definitions, okay? And remember this test we'll talk about it tomorrow, and I'll email you guys tonight. But this test that we're doing this time is going to be a lot different from the last ones that we just did. It's going to be everything is going to be fill in the blank, not fill in the blank, short answer, or like you write out your answer. So it's only going to be like a couple questions, but there's no multiple choice. And it's going to be more of a take home, like before I was having us do it at like real time, but this one I'm going to have you take it home. So yes, so for example, if there is a question that says write the definitions, or like what are the different conditions that affect the rate of reactions, and define them, these are the different things that affect the rate of reactions, and these would be the way that you would define them, okay? So that is your friend. All right, so let's keep going. Okay, collision theory. So the collision theory states that in order for a reaction to occur, reactant molecules must collide in the proper orientation and with sufficient energy. Okay, so in order for this reaction to occur, they must collide, right? So these molecules must collide. They must collide, right? In order for a reaction, they have to run into each other, right? Otherwise, how are they going to hang out? How are they going to share? How are they going to give and take electrons? They have to be near each other, so they must collide, right? But they must collide, number one, in the proper orientation and with sufficient energy. So for instance, the way that this is situated here, right, there's this one orientation and this other orientation. So this is saying, okay, this is the first orientation here, you have the second one, so this would be the proper orientation, right? Because depending on the things that you're connecting together, if there's certain molecules, right, well, we know that we have the concept of repulsion theory. So obviously likes repel, opposites attract, right, and likes repel. So in that, they're going to have to make sure that they're in the correct orientation so that they can make the proper connections. But in order to do that, so they must collide, and they must kind of move themselves so that they can collide in the proper collide in the proper way, or actually collide. So they come together, they kind of turn, and then there has to be enough energy for this reaction to take place. So like we were saying, previous examples when we talked about chemical reactions, you can add heat. It's like some reactions, right, you're going to have exothermic, where it's going to release heat in order to create the chemical reaction, and some of them are going to take in heat, right, in order for a chemical reaction to occur. So basically the collision theory is saying that in order for a reaction to take place, there must be a collision that is in the proper orientation and have enough energy to come together. So they must collide, move, and have to be energetic, okay? Enough energy for that reaction to take place. Okay, so this is kind of a good, like a summary of kind of the energy diagram of the concept of the collision theory. So, like it said earlier, this states that in order for a reaction to occur, reactant molecules must collide in proper orientation and sufficient energy. So, what does that really mean, like when we say sufficient energy? So, in this example, right, we have O3 plus NO, right? And so these reactants must collide with an energy at least equal to EA. So every reaction is going to have a certain amount of energy that it must overcome in order for a reaction to take place. So this energy barrier is called the activation energy. So this EA here is the amount of energy that is needed for the reaction to take place. So it will not, if it doesn't get this much energy, this reaction will not take place, right? So if you don't increase temperature or energy somehow is added to this in order to push this reaction forward, a reaction will not happen. So, and so this basically right now, you have these together, and then in order for it to come down to these products, it's almost like you have to push it all the way over this little barrier to get to the products. So you need energy to go over this barrier. Okay, so, but in between how it has this activated complex, right? So the activated complex is that saying like, well, before we actually get to the products, when we're creating enough energy in order to create the products, we have this point where all of the compounds or elements are connected together in a complex called the activated complex. So basically, once we have at that peak of the activation energy, we're at the peak of the barrier. Now we have all of our compounds. We have enough energy for all those pieces to kind of fit together, right? But obviously, we know they don't stay all together, right? We have our products. So it has to all come together so that it can be near each other so that it can create the reaction to have these specific products. Okay, so hopefully that makes sense. We're going to continue to talk about this with other graphs. Okay, so each reaction has its own energy diagram. So like I said, so you need to understand that when you see this is what you would call an energy diagram. Okay. So each reaction has its own energy diagram, which shows the amount of energy required to form activated complex as the reaction progresses. So this is how it progresses. That's the x-axis, and the y is the amount of energy that is needed in order for the reaction to actually take place. So this activated complex, like I said, is the kind of in-between part before you get from your reactant to your product. So it shows you how much energy is needed to get to this activated complex. So the activated complex is kind of the peak of the amount of energy that's needed to go past the barrier in order to go to the products. And that intermediate is when we're all, not intermediate, kind of in-between areas when they're all near each other, right? We finally had enough energy for them to be together so that they can finish this reaction. So this is every single reaction that we have will have an energy diagram like this because there's a certain amount of energy that needs to be overcome in order for the reaction to take place. Okay, so, and this is just more into that. So activated complex. So it's a short-lived, unstable, high-energy chemical species that must be achieved for the products before products can be formed. Formed from reactant molecules that collide with the proper orientation and sufficient energy. So with following the collision theory, right, that's how they collide. So that's how the products are formed, right, through the collision theory, because that's the definition. And the actual structure is unknown. So this whole complex is created through collision theory, right? So this collision, they need to be near each other in the right orientation so that they can begin that process of reacting and with sufficient energy. So this activated complex is short-lived and unstable. And that makes sense, right? Because is this our product? No, right? It's not. It's just the midway point. It's kind of like, okay, now we finally had enough energy to get all the players in the game, right? And so now that we have enough energy to have all the players in the game, we're not stable because like now we're near each other. Now they're all the pieces are near each other. So they're like, oh, okay, now we're all near each other. Now let's go to the ones that we want to be near. So we're all near each other, but it's not stable because that's not where they should be. It's not the proper location. But now they're at least in vicinity of each other so that they can recognize and say, hey, you know what? You look like a good partner. Hey, you look like a good partner. Now we're near each other and we're at the highest area of energy and we can see these things. And now we can connect and go and create our products, right? So it's unstable. But it's a high energy level, right? Because that's the highest energy level area. It's kind of the peak of that activation barrier. And it's short-lived because it's quick. It's not where we're going, right? It's that transition. It's just like at that peak of the energy, this is where they all come together so that they can begin the reaction. Okay. Hopefully this is all making sense. All right. So reactants must overcome an energy barrier before they can change to products. The minimum amount of energy needed to overcome the energy barrier is called activation energy. So know this definition. And this EA is what activation energy means. So if you see EA, E sub A, then you know that's going to be activation energy. Okay? So remember that's the minimum amount of energy needed to overcome the energy barrier so that the reaction can proceed. So this space that goes from where you started to the activation complex, it's almost like a little hump, right? You have to get these over this little hump in order for the reaction to take place. And that little hump, the amount of energy that it went from to get from this the reactants to the highest point, i.e. the activated complex, is going to be the amount of energy that is needed for the reaction to start, right? Because once you get to the activated complex, you know you're at the highest point of the energy that's needed for the reaction to take place. Because now, what did you want? You wanted them to all be together. So now that you have them all together, that's going to be the highest point of energy. You don't need to add more energy once you've got them all near each other. So now once you have them all near each other, now you can have a reaction to take place. So that's why this is going from the reactants to the activated complex, because once you're at the peak of the activated complex, you don't need any more energy. You already achieved the reaction, I guess I should say. It already achieved what it wanted, right? It already achieved putting all of these molecules near each other. So once now it's like, okay, I've achieved this. I don't need any more energy. So the total amount of energy that I needed is going to be from where I started at the beginning, right, with the reactions, like your initial, and then your final energy kind of would be like where the activated complex happens. And so that area, that space between these two is going to be the minimum amount of energy needed to overcome. So you need at least this much energy in order for this reaction between these two molecules to take place. Okay? Reactions with large activation energies tend to be slow because a relatively small fraction of reactants have sufficient energy and sufficient energy for effective collisions. So if you have a large activation energy, right? So the space from here to here is very large, right? So that's what this is saying. This large activation energy. So this could be a big thing. It could go like this, right? That would be large activation energy. So yeah, that reaction rate is going to be slower, right? So because what? You have to push this. It's almost like you have to push these molecules over this high hill versus having to push them over this, right? So this is going to be like a smaller activation energy, and this would be a larger activation energy, but it's going to be slower reaction rate because you have so much more of a barrier to go over in order to start the reaction, right? So if you have a larger activation energy, you're going to have a slower reaction rate, because there's the small fraction of reactants have sufficient energy for effective collision. So there's not a lot of the reactants that are over here that have enough energy really by themselves. So it's going to take a long time, okay? Hopefully this is all making sense. All right, so let's go look at some other energy diagrams. Okay, so we've talked about endothermic and exothermic several different times, right? So the concept of endothermic and exothermic is the same. We're just applying it in different ways into different concepts, right? So here we're talking about endothermic versus exothermic in terms of energy diagrams, because what is everything that we're saying we've been talking about, right? What needs to happen for a reaction to take place? We need to have them collide with the proper orientation, right, but also with sufficient energy. So that means there's going to be certain reactions that are going to increase in energy or decrease in energy, right? So there's a certain amount of energy, right? It just depends on which direction you're going. So when you have an endothermic, so this is the graph for the end. So these are, you're going to have to know what these look like. That's all I would want you to know for this section, is just know that this is the chart for endothermic and this is the graph for exothermic. So in endothermic, well, what is endothermic? That heat is going indoors, right? Indoors. So the heat is going indoors. So that means that if our reactants are starting with low energy, right? So we're starting with low energy and we're adding energy into our reaction for our reaction to take place. So if you're adding energy into the system, to the reactants, that means you're going to have an endothermic reaction. So as we start with the low energy and we add energy, and so as we're adding energy into this reaction, right, adding energy, we're increasing in the energy in order to get our product. So the reactants are lower in energy than the products for the endothermic, right? Because you're starting out with not a lot of energy, and you added, which is endothermic, you're adding it into the system to get the product. The exothermic is you're starting out the opposite, right? Because what is exothermic? Exothermic is the energy is exiting the system. So in that, we're starting out with our reactants with a very high energy, right? So the reactants have high energy. Start out here. Because the concept of exothermic is what? So you have heat already, and the heat is leaving the system. So for the heat to leave the system, you have to start with heat in the system. So the system is our reactants. It's starting with heat, and then because it's considered an exothermic reaction, it's going to decrease. It's going to lose heat in order to create the products. So the products are lower in energy than the reactants. Okay, so just understand the difference between the two charts, right? So endothermic, the reactants are lower in energy than the products, and then exothermic, the products are lower in energy than the reactants. Okay, so let's practice. Always so much fun, right? Okay, so let's see. Okay, energy diagrams. The following reaction is an endothermic reaction. So you have 2 moles of nitrous gas, 2 moles of mononitric, and 1 mole of oxygen gas. Draw a energy diagram that shows the relative energies of the reactants, products, and activated complex. Label the diagram with molecular representation of reactants and products and possible structure of the activated complex. Okay, so basically what they want us to do is use this diagram as an example of how we're going to, or what we're going to draw. So that's basically what this is asking, is for us to draw the energy diagram, right? And this is the energy diagram, but it's used for any type of chemical reaction. So we're going to draw it for this chemical reaction. Okay, so I'm going to go back to the question so that we can look at that. So it wants us to draw an energy diagram for this reaction. So we have our Y, we have our X, and so we're going to be increasing. Energy. And then progress. Okay, so this is energy, increased energy, right? And then you have your reaction progress. So we are starting, so when you first look at this, what is the first thing that stands out to you when you read the very beginning? The following reaction is an endothermic reaction. Like even before you look at the actual reaction, you should say it to yourself, okay, well, what did we just go over? And in what direction am I drawing my graph? Sorry. So we know that this is an endothermic reaction. Endothermic. So we're going to be having the reactants starting low and the products ending high in energy. Okay? So in that, we write this as let's see. If we're going to start with the reactants low, so we're going to start low and end up high, right? Let's just say. And it doesn't necessarily matter to scale, right? But we know that it's about something like this, right? So that means that we're going to have, let's see, we're going to draw our chart. Oops. Let's not draw them so far away from each other. Let's do this. Okay, so you might have something like that. Okay, it's not the best little loop-de-loop thing, but this is kind of what we're doing, right? Because we're going to be going from the reactants. We're adding more energy. So if we're adding more energy, our reactants are going to have to start out lower, right, than our products. Because if we're adding energy, then we should be up here when we're done, right? So let's go back to the actual problem. So this is the actual problem. I'll write it up here too. Okay, so what are the reactants in this equation? Nitrous oxide, right? Okay. 2. Okay, right? You have your NO2 gas. So then you're going to have your products, which are 2NO2. 2NO. Plus, okay, so those are your products. So it wants us to draw an energy diagram that shows the relative energies of the reactants to the products, right? So this is how it's relative because you have less energy in the reactants, more energy in the products. And the activated complex and then label these things. So let's see, so the activated complex, so where is the activated complex supposed to be? What point of this chart has the activated complex? This top area, right? Because remember the area, like you want to think that the height of the energy is where it's full activation. So when it's activated, that means it's at its peak of its energy. So activation, it's only activated, like you're only going to have the activated complex when you're at the peak. So activation only happens at the peak. Kind of a way. So if this here would be the activated so this could be, let's see if you just did an O. So then if you were to represent this in terms of molecules, you would have your it kind of be, it doesn't like the activated complex doesn't have to be necessarily right something that is perfectly written out, but just to show what's kind of happening right now. Right, so let's just say that's my activated complex. I hopefully you can see that. So I just wrote like N, this is 2 NO2s, right? So it's just more so that you're kind of showing that these are all kind of connected together. So you can, I mean, another way that you can write it is just to have lines, and you can say, right? So you can do this. You could do something like that too. You know, just it really doesn't matter what it looks like because it's an unstable, very temporary molecule, right? That's really just saying that these molecules are all together, you know, or you know, in this arrangement and at the activated complex. So as long as this is kind of how you draw this, just lines. It doesn't matter where they are, just kind of lines of these, the number of having the correct number of particles, of course, going forward. So this is the final kind of product that I would want for this answer. So this would be, we have our relative energies, we have to the reactants and products, we have our activated complex, and, oh yes, but I guess we have to label this. So what we need to write here, that I forgot to write, do this. Okay, this is the activated complex. This is the reactants, products, and then so. If you remember, we also need to describe or show the location of the activation energy. So the activation energy is going to be from the reactants to the activated complex. So from here all the way down to here, right? Okay, so remember, because what is the activation energy? The amount of energy that the reactants have to go over in order for the reaction to take place. So it's always, even though this would be higher, right, in energy, it's always based off of how much energy the reactants need to get over to the products. So this area would be the EA, which is the activation energy. Okay, so I lied before. This is the final product of what you would have written out for this this answer, because you're showing the energy difference between the two, but you want to also label that you know what you're saying, like you know what you're talking about. You know that this is the reactants, these are the products, and draw the difference between the reactants and the activation complex. Right, the difference between that is the activation energy, and at the very top of this chart is the activated complex. Right, it's at that point of that you know the amount of energy you need for this reaction to take place. Now it's all together, so now that we have the amount of energy we need to put it all together, the reaction will take place, okay? Okay, so hopefully that all made sense. Okay, let's keep going. Okay, so this is another example. So practice solutions. So energy diagram. So this is another example of what should we call it? An energy diagram. Okay. Right. So here we're saying that the amount of energy, right? So you're starting with this on this side is where you're going to actually have the reactants, and this side you're going to have the products. Okay, so I know that it's a little backwards, but so just even looking at this chart, you can tell that here, right? What are we starting out? We're starting out with one compound. So here's that one compound, right? And then this is broken into two different elements, and so on this side, that's where we have that, right? So that's just FYI. Okay, so here we're starting with the reactants, and then we're going to the products. So this is just another example. So if we're going to the reactants to the products, so what is this area called? Activated complex, right? Okay, so you have your reactants to your products, and you have your activated complex, right? This area is the activated complex. Okay, so now what do we need? What else is it that we need to label on here? We need to say how much energy was used, right, in order to get from the reactants to the activated energy. So we would label that being from here down to here. Okay. Okay, so this area here, right from the reactants to the activated complex, is going to be the EA, which is the activation energy. Okay? So also too, when you're looking at your products or you're just looking at the reactions and you're looking at the direction or kind of the type of reaction that's happening. So like what kind of reaction is this? Well, this is a decomposition reaction. So in the decomposition reaction, what kind of energy reaction do you think that would be? Like, would that be releasing energy, or would it be requiring energy to break something down when something's being broken down? It's releasing energy, right? So that's why, right, you're going to have this lower, oops, I'm sorry, this is, Yes, this is, sorry about that. This is backwards. So this doesn't feel right. I don't know what I'm saying. So this is products. Because we're releasing energy. Da 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 da. So products, and then you have your amount of energy that is used that you have to get over, which is this is the EA. So from here to here is the activation. Activated. Okay, yes. Sorry about that. That feels better. I was wondering, something felt off. So, yes, we have our reactants and then our products. So that's why this is going to be lower than our reactants because we're going to be releasing energy here. Okay. So between these two examples, hopefully that made sense. Okay. Okay. So now let's go into the rate of concentration effect on rate of reactions. So, reactant concentration effect on reaction rates. So we talked about like temperature, right, which is kind of like energy as well. It's going to increase in the temperature. Temperature is kind of another form of energy. So we talked about the temperature, and now we're going to talk about the reaction concentration, right? Because we're going through all the different factors that affect the reaction rates. So reactant concentration effect on reaction rates. An increase in concentration of one or more reactants increases the number of reactants per unit volume. More molecules are thus closer together, and the number of collisions per unit time increases. So if you're increasing the number of molecules, right, they're going to be closer together. So like for instance here, you have a small, there's only a couple, right? So the rate, how quickly this could like connect to here and this could connect to here, right? It's going to be slower than these connecting, right? So increasing the concentration, increasing the number of particles that are in the solution is going to be quicker connections because they're closer together. So if you have more of them, the closer they are together, and the faster the reaction will occur. So that as total collisions increase, the number of molecules with the energy and orientation required for the reaction also increases. So it's kind of the same thing. So if your total number of collisions increases, that will increase the rate of reaction, right? So the more that they're hitting each other, the more that they're like, oh my god, I can react. Like, hey, I can react. So if I collide, now I'm going to have a reaction. So if I'm creating more collisions, the concept of the collision theory is the concept of the reaction taking place, right? And the things that you need in order for the reaction to take place. So when they collide, a reaction is going to take place. So an increase in the number of collisions increases the rate of reaction. The fraction of effective collisions remains the same because the temperature and kinetic energy are constant. So the number of collisions is going to stay, but it's going to increase. But the temperature and kinetic energy are constant. So there's nothing that's basically affecting this except for the number of molecules. Okay, so just remember the important thing here is that the increased concentration, right, which is basically it's also going to create an increase of collisions, which is therefore going to create an increase of reaction. Okay, so now let's talk about temperature effect on reaction rates. So the temperature effect on reaction rates. So the average kinetic energy of a substance increases as the temperature increases. So how quickly these substances move around increases when the temperature, right? So if you're like, if there's basically you put a fire under a solution, as that temperature increases, some of those particles might be kind of moving, but then all of a sudden they're like, oh my God, it's hot, oh my God, right? So as you're increasing the energy, as you're increasing the temperature, the kinetic energy, which is the moving energy of those molecules, increases. An increase in kinetic energy causes the reaction rate to increase in two ways. So an increase in collision rate is one way, right? So if you're going to change the temperature, so if you're increasing the temperature, for instance, like a gas, what's going to happen to those gas molecules? They're going to move around. And if they're moving around faster, they're probably going to run into each other more frequently, right? So you're going to increase the rate of collision rate, which therefore is going to decrease the rate of reaction. So molecules move faster at a higher temperature and therefore collide more frequently, which makes sense. So it's like if I'm moving around, these particles are moving, they're slowly moving, like they could eventually maybe run into each other. But if they're quickly, like they're going to probably run into each other a lot sooner or faster, right? And then the second way is increases the fraction of effective collisions. So the more of the molecules attain activation energy because the average kinetic energy of the molecule increases. So they actually are able to get more energy in order to for the reaction to take place. So remember, the activation energy is the barrier, right, that it needs to get through. So basically, this is saying that if you increase the fraction of the effective collisions, which means more molecules attain an average, an active activation energy, because the kinetic energy of the molecules increases. So the activation energy, they're able to create more energy. So because they're moving around and they're creating more kinetic energy, they themselves are going to be more energetic, and they themselves therefore are going to be able to increase that energy that is needed. It's going to basically increase the amount of energy that they have so that they can go over that barrier itself, right? So it's like if they're moving around, they're like, oh my God, I'm moving, oh my God, I'm moving. So that's in itself, like when you're moving around, right, because it's hot, you're moving around, you're also gaining more energy as you're moving, right? You're gaining more energy. So as those molecules are moving, they're gaining more energy. And like we said, for a reaction to take place in the collision theory, it needs to collide in the correct orientation and with sufficient energy. So increasing the temperature is going to make those molecules move more, which is going to increase the kinetic energy of those molecules, which therefore is going to make those molecules react quicker. Because now it's like, oh my God, I have more energy for me to get over this barrier. Before I didn't have as much, but because now I've created my own energy by moving around, I now have enough energy to help myself go over this hump. Okay, so that's kind of what this second part. So first is the temperature is going to affect this. Like the higher temperature is going to have a lower activation energy. Lower temperature is going to have a higher activation energy. Okay? Okay? So hopefully that makes sense. Okay, so here we have, you know what, actually this is going to go into the catalyst section. So I'm actually going to go ahead and stop here because I'm going to begin to talk about catalysts and finish chapter 12 in the next lecture. Okay? All right. Well, I will see you all tomorrow.